Today we're going to talk about the infinite limits. Limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Here we have a sort of epsilon delta kind of definition for what this means. Essentially, it means that we can make this function value as large as possible or as small as possible in the negative direction, just by getting closer and closer to the number c. And so we have a similar definition here as we do for the limit, as x goes to f of x and equals a finite number. So this basically is showing us that the limit does not exist when this happens, and it's showing us why. Because it's heading to infinity. There are other reasons why limits don't exist, we know that. But this is one of them, and here we have a precise meaning for this when this occurs, precise definition for this situation as it occurs. Now we can alter this a little bit here for when f of x approaches negative infinity. Very similar, just that a value n can be found no matter what. Whatever n is given, we can find a delta such that that f of x will be less than n whenever x is between c and delta. In this case, wherever that is, plus or minus delta away from c. That's what this is saying. And also says that we don't want x to be equal to c. That's what this zero tells us. X cannot be equal to c in the definition. Okay, and limits from the left and right are replaced with these. This is for the limit at the left, so we replace this expression with this one. So any x in this interval will imply that f of x is larger than m. All right, let's look at a proof here. For example, proof problem. We'll start off with our. Let's just restate this idea. Okay, so what does this mean? It starts by saying, one way to say it is that if any m greater than 0, there exists, oops, okay, yeah. M greater than 0, there exists, it's a backward E. There exists a delta greater than 0, such that if is less than x, less than 1 plus delta, then 2 over x minus 1 would be greater than m. So what it's saying is that if this is true, then we should be able to find a delta greater than 0, such that if x is in this interval, then f of x will be greater than m, no matter what value of m is placed in here. So to prove this, what we're going to say is, we'll start with a function and start with this and see what does this imply. This is our final statement here. So this is where we're starting on this one. What does this imply about x? Well, let's see what it implies. Let's see, we could say 2 is greater than m times x minus 1. Now, no, this is positive because notice that x is approaching right in here. We're assuming x is bigger than 1. So we'll be coming from the right side, so our proof will hold for x greater than 1. So we have this statement, and then this says that 2 over m is greater than x minus 1. No, that says that x, so that's the 1 plus 2 m. It's uppercase m. And now we already know that x is greater than 1, so we can throw that on. And that means that this should look familiar. Notice how similar it is to this statement. These two. The only difference is that I have a delta up here and I have a 2 over n plus here. That leads me to think that I'll just let delta be equal to 2 over n. And you could be smaller than 2 over m, but it's only necessary that it's no bigger than 2 over m. Okay, it's only necessary for the proof. So this would be our delta, this size, and this would do the job. The proof is in walking backwards, starting with this delta, as your chosen delta, walking backwards this way, starting here. In other words, starting with this, if this is true, so it would start with this, and work your way back upwards this way to this statement. And there you have it. Okay, so 2 over x minus 1 would be greater than m as long as I begin with this delta and this statement here, starting with this. Okay, so that's a proof for that. Now, let's look at some of the other particulars here. I don't want to get too involved. I don't want to make this video too long, so let's continue. The vertical asymptote is precisely one of these limits. If there is a value c where this occurs, then we would say that if either one of these occurs, then there's a vertical asymptote at x equals c. And here's another theorem involving the vertical asymptote. F and g are continuous functions on some interval containing c. With f of c not 0, well, g of c is 0. And if there's an open interval containing c where g of x is non-zero for x not c, then f over g has a vertical asymptote at x equals c. So that's a kind of intuitive result we've seen already. Let's look at here, where do we find these vertical asymptotes? Well, you search for them at where that denominator becomes a 0. And the numerator is not 0. Notice 1 would never be 0. So these are the two things you look for if you're trying to find vertical asymptotes. Set the denominator to 0, and then we'll solve that. 3x is -2, x is -2/3. And as long as the numerator is not 0 at the same time as the denominator, you have a vertical asymptote. So we have one here. And here's another one. Let's see. Start with that denominator again. Is that 0 anywhere? Yeah. Oops. It's 0. Okay, it's 0 at plus or minus 2, which means, now look at that numerator. That numerator is never 0. So let's make a note. X squared plus 4 is not 0. It's x equals plus or minus 2. So vectors would never be 0 for any real numbers. But So there we have two more. We have two vertical asymptotes, VA and x equals plus or minus 2. Remember back over here we had VA and x equals -2. Here we have another one. H is equal to the cosecant. Now, remember that's 1 over the sine of x. So all we need to do is indicate and locate where is the sine of x equal to 0. And if we remember, x would have to be some multiple of pi for that to happen, or n is an integer. Okay, and an integer. So that's where your vertical asymptotes would be. Notice the numerator is never going to be 0 for this function. So that's it. Those are your vertical asymptotes right there. Okay, let's continue. Now let's find these infinite limits. Okay, now to find these, notice a direct substitution would be your first approach. If you just throw in an x equal to 4. For this first one, you would have an 8. And here you would have, this would be heading to 0. So that means we have an infinite limit. Question is, now we know this doesn't exist. There is, in fact, a vertical asymptote there. Is it plus or minus infinity? So we see it heading to infinity, since the denominator is 0 and the numerator is not. And they are continuous functions, both numerator and denominator. So we see it's a vertical asymptote happening. The question is it positive or negative? Well, just look at the value of that denominator. Notice when x is less than 4, that makes that denominator, it's heading to 0, but I'll just say from the left. In other words, it's negative. Okay. Since x is heading to 4 from numbers less than 4, and you're subtracting 4, you're going to get a negative denominator. So that's negative in the denominator. Now the numerator is definitely positive, no question. X is heading to 4. It's a little less than 4, but that's still a positive numerator. So then we look at that also. So we have the numerator heading to a positive. So we can summarize this. We have numerator heading to positive, denominator heading to 0, but it's negative. So overall, we have a fraction which is less than 0. Okay, now admittedly, it's heading to something large and negative. So it is still less than 0. So this is negative infinity. Okay. So that's very specific as to what's happening to this. Now this one, same thing's happening here. We've got an 8 up top and we get a 0 on the bottom. However, the 0 is heading to 0. This denominator is heading to 0 from above 0. In other words, it's bigger than 0, but it is heading to 0. So we've got a positive over a positive. That makes plus infinity for this one. This next one, the numerator is always 3. The denominator is heading to pi over 2 from above. So these are numbers bigger than pi over 2. And you kind of have to think about the cosine function here, what's happening. Think about the values of the cosine in the second quadrant, possibly in the unit circle if you want to picture that. Or you can just view a quick little sketch of the cosine. Okay, we all know this little sketch. This is 2 pi, and this is 0 here. So here's pi over 2. So what this limit is actually looking at is for the cosine function, x is heading to pi over 2 from above. So in other words, I'm coming down the line this way, coming down this way with my x values. And that means my function points are here. But the point is, they're heading to 0, and they are negative. So I'll indicate it that way. So we have a 3 in the numerator and numbers in the denominator, negative, getting closer to 0. So we're saying this is going to be negative infinity. Okay, so that's about it. I mean, that's a simple way to evaluate those. Let's see, what else do we have? I guess that's it. Okay.